So then, hello, everybody. I guess I know most of you. Maybe we could just, could the two of you introduce yourselves, if you don't mind?
I'm Eric. I'm in the McDermott group. So really,
Great. And I think you know everyone else. So today I'm gonna, so first, this is my first time teaching in this course, and I'm probably not calibrated perfectly because I didn't do my job to read back on what I taught you and previously. So if my lecture is a little bit off, that's okay, because you'll tell me and I'll fix it next time around in terms of the depth. So I didn't know whether to go into product operator formalisms and
all product operators, and they know a lot about the dipole.
Okay, well, next time I will give the Wigner. So I wasn't sure whether to give the Wigner talk or to do the more classical talk. So I'm giving the classical talk, but maybe actually for the next lecture, maybe for tomorrow, we can come back and go through the treatment of the dipole interactions using the Wigner rotations and be more rigorous about things. So today it's more going to be about just RDC. So I'm going to talk about residual dipole couplings, and I'll give you like an overview of the whole technology and how one measures these things, and with an emphasis on nucleic acids because you had enough proteins, I'm sure, over the course of the various lectures. So as probably all of you already know, the dipole coupling is an interaction that's given between two nuclei through space. And I'm showing you here the interaction between a carbon and a proton nucleus, separated by a bond length r distance. And of course, this bond vector makes some kind of angle with respect to the magnetic field. And in the laboratory frame, the dipolar coupling that we would write down is given by the expression shown here, where we have the angular bracket around the d cos squared theta minus 1/2 term to indicate that we're taking a time average over all the orientations of theta, which are sampled by the molecule in solution. We have a R quadratic term, inverse quadratic term to the distance. And then we have the gyromagnetic ratios. So the bigger the gyromagnetic ratio, the dipole coupling scale linearly. And then we have a bunch of constants. Okay, now, normally under isotropic conditions, what happens to the angular term? So so the angular bracket denotes the fact that my molecule samples many orientations in the solution. And if I average over, the measurement that I'll make will be averaged over some time scales. And if I do that, then the resulting measurement that I make will be given by the average. So how would you compute the average of this function? How do you compute the average of any function? Yeah. Okay, but what is, so let's say, correct, you want to integrate, but what is it just straight out integration of the function? What's the integral of d cos squared theta? So, yeah.
Sine theta.
Why did you say sine theta?
The weight for being in the
Right, so if you wanted to ever compute the average of a function, the way to do it is you want to integrate the function times the distribution function. So I need to calculate for every given theta angle, what is the fractional weight multiplied by the actual function where I compute the value, and then take the integral, which is to say to sum over all values. Now, you just mentioned that the distribution, so this is interesting that you moved quite quickly. But if I have a random distribution, if I have a bond vector and it is in my map and I have a magnetic field, and my bond vector is allowed to sample every orientation with equal probability, what is the most probable theta angle between the bond vector and the magnetic field? Now, you should answer, oh, all the thetas are equally probable, right? Because my bond vector is randomly oriented, right? So there's no biasing force whatsoever. So a naive answer would be that, oh, all theta angles are equally likely. But that's not true. And why is that the case? Why is it that certain thetas, certain orientations are more likely than others? And which one is the most likely? I mean, you kind of answered that question, but anybody else have an idea of why why is it not just equally probable for every orientation? For every theta? No, and by the way, no trick question here. Forget, forget like NMR. I have two vectors, I have two vectors, and I'm literally saying there's an angle between two vectors. I take this vector in three-dimensional space, I say it's allowed to be anywhere with equal probability. What is the distribution of theta? Is every theta angle equally alike? There's no NMR trick here, it's just pure vectors. How many ways can I be pointing this way? How many ways can I be 90 degrees? Got it. Right? So lots of ways of being 90, very few ways of being 0. And then a little more, a little more, a little more. What's the function that describes that distribution, which is maximum at 90, minimum at 0? Yeah, what is that? God, that's Gaussian. Where did Gaussian come from? Geometrically, there's no Gaussian. There's this. What's the measure of the radius traced by the vector? So minimum at 0, maximum at 90. What's the function? Sine theta. So sine theta. So it's actually most likely, if you were to leave the room and come back and capture the vector, right? And the most likely thing to capture it is to be perpendicular, right? Because there's lots of ways of being perpendicular, but only one way of being parallel. And so therefore you have to take the integral. Now, t cos squared theta minus 1/2 is a function that starts up. What's the maximum? When the value of theta is 0, you get +1. And then when the value of theta is 90, you get -0.5. Right? So it's like 1 to -0.5, right? So you can see that the -0.5 is compromised because it's only -0.5 versus a +1. When you multiply it by sine theta is biased against the theta equals to 0. So it takes away from the +1s and gives a little more to the negatives. And when you multiply the two and take the integral over that new function, the sine theta times t cos squared theta minus 1/2, you'll have equal pluses and minuses in the function over the 0 to 2 pi interval. And so the average is 0. And that's why all anisotropic interactions, which are dictated by the same p to 0, t cos squared theta minus 1/2 function, this is the same function that underlies the average orientation of the CSA tensor. What else is an anisotropic interaction in NMR? What other interactions are so-called anisotropic interactions that depend on the orientation of tensors relative to the field? This is the dipolar coupling, where the relevant tensor is the dipolar tensor, which is basically just the bond vector. The CSA, which is a different tensor, also averages to 0, so that you only measure the isotropic chemical shifts. Same functional form. What other interaction in NMR is anisotropic? Any idea? Quadrupole couplings are also isotropic, and they also average to 0 because of the same description we went through now. Okay.
What about chemical exchange?
It averages to 0.
How does it depend on orientation? That's right. It's independent. Doesn't average to 0 because there is no orientation. Or if we thought of it, we wrote it in terms of spherical harmonics, it would be the spherical harmonic ring 0, 1. That's spherical harmonic is unity.
So these are the second rank interactions that we're talking about here for the isotropic part. It's good that you guys went that deeply. Next time I'll carry on from there, but it's okay. Today we'll go over classically, and then tomorrow jump into something else.
What else can I put in?
A great question. So you're asking, are scalar couplings, they're isotropic and they're averaged to 0, but there is something called, there is a component of scalar coupling. I don't know if you know about this, right?
There's an anisotropic.
component.
Anti-symmetric.
Yeah, what is it called? What is it?
No, it has
It has a special name. There is an
so it
anisotropic.
doesn't show up in normal NMR.
Yeah.
If people like difficult.
Yes.
Measure.
Yeah. Secular couplings of the second kind. There's like, the scalar couplings of the second kind, that these are the anisotropic components of scalar couplings, which you normally don't observe, but there are people that are trying to, as Art said, like investigate the consequences. They might have consequences to relaxation, but I don't think they are manifest as energies changes, as changes splitting, Yes, the scalar coupling can be also isotropic. All right, great. So now just to give you a picture of, if you wanted to visualize dipole coupling so you can feel very good about it. Literally, this is the interaction of two magnetic dipoles if you bring them next to each other. And what I'm showing you here is I have a spin I, this could be a nitrogen, and spin S, which is the directly bonded proton. So the proton is a little magnet, which is either in the alpha state or in the beta state. So if it's an alpha state, it's pointing up. In the beta state, it's pointing down. And the magnetic fields that are coming out of the nucleus of the proton generate a local field at the spin I. And so, for example, in the top left, let me see if I can use the cursor. I'll just say, here we go. Pointer options, visible. Oh, sorry. So here the nitrogen experiences the local field from the neighboring proton, which is opposing the magnetic field. And so it's causing a reduced effective field at the spin, and as a consequence, it resonates upfield a little bit because of that local field. Whereas in the situation where the nitrogen, the proton neighbor is a beta state, it's pointing down, and then the magnetic field now reinforce the magnetic field, so you have a little bit of an upfield shift to the resonance. And so the local field at the nucleus changes as a consequence of the local magnetic field. And as you can imagine, if I bring the nucleus closer, the density of the magnetic flux grows the closer you are to the nucleus, and it grows as the inverse distance power 3. And so therefore this differential, which is the dipole coupling, is this difference between the two. Just like a scalar coupling, you're associated with the spin up or spin down of your partner. If I bring the nucleus closer, I'm like yes, this is obviously a through space interaction. They don't need to be bonded to feel each other's magnetic fields. If I bring them closer, then the splitting grows. And of course, if my molecule tumbles, the quantization of the spins always stays up and down, right? Just because your vector is, when you think of a vector rotating, it's doing this, right? So the quantization remains up. But now, of course, the nucleus finds itself in a place where it's enjoying double lobes, two magnetic fluxes coming together, right? So if you will, there's a greater, it's almost twice, right? Twice the amount of local field is generated, and it's going the opposite direction relative to when it was here. Here it was being opposed. Now we suddenly find that it's reinforced and twice the magnitude. There's two lobes, and that explains why you get a twice the size of the dipole interaction when it's parallel versus when it's perpendicular, and why the sign is also flipped. So +1 for the 3 cos squared theta minus 1/2 versus -1/2. So this is a classical depiction of the dipole interaction. And of course, which resonance is blue and which is red would depend on the gyromagnetic ratios of the spins. And I don't even know if this is correct for a proton and nitrogen, but nitrogen has a negative gamma, so if this was carbon, proton, then I would have to switch the color labeling.
And I quiz the subfractions that are in biophysical chemistry once.
Who's in the biophysical chemistry?
This week.
How's this?
That's we could actually be effective.
Yeah, but there's still dipole interaction. Still 1/r². And then the second order interaction, so it ends up being 1/r6. All done. But what's different? Something really important different. She pointed out in the castle. What's the tricky thing to know, Fred?
Orientation.
Capital, right?
Yeah,
The
that's-
orientation of the dipoles, which can be oriented, who knows, in space. But here, the dipoles are always polarized along the
I never appreciated that part.
There's
That's a
no
great
cap.
point. Yeah, thanks to the very expensive magnetic field. We don't have kappa. I didn't know that was the reason we had a magnetic field. To get rid of kappa. That's such an interesting point.
It's the same thing.
Well, that's only if they're randomly oriented. You don't know.
Yeah. Okay, and of course, by the way, where on this, where does I need to be in order to feel no contribution from the magnetic field? So you can see right over here, the stray fields from the S spin are roughly perpendicular, right, to the magnetic field, which means that the partner is is having no consequence on the field. And so what is that angle? That's your magic angle. You know, so that's 54.5. And it's a magic, it's magic because of the fact that it actually is the place on a magnetic flux where your direction is aligned like that. Okay. So therefore the angular dependence can be, literally the angular dependence and the distance dependence can be understood. It's just a classical description of a magnetic flux emanating from a magnetic bar. Okay, so now, of course, it's wonderful that dipole couplings average to 0 for solution state NMR, because that's why solution NMR enjoys the high resolution that it enjoys, is a consequence of not having dipole couplings as you might have in the solid state, where your molecules are not averaging to 0. Instead, you have lots and lots of dipole couplings. I'm being dipole coupled to all my adjacent nuclei, and that creates a great deal of complexity. But in solution NMR, dipole couplings and other anisotropic interactions average to 0, giving us the wonderful high resolution spectra. And solid state NMR folks spend a ton of time trying to get rid of dipole couplings by spinning at magic angle at faster and faster speeds, just to look like solution NMR. And so you could ask the question, why don't solution NMR, why don't you take solution NMR, make it a little bit more solid? For once, like, you know, let's go the other way. Let's go from solution to solid, but maintain the resolution of solution NMR. Now, to do that, if you can take your molecule and break the randomness of the orientations, and you make the orientation anisotropic, so the molecules somehow align, but not to the tune of solid state, where it's 100% aligned, but rather a small fraction, then one could reintroduce the anisotropic interactions, including dipole couplings, but maintain the resolution that solution state NMR enjoys. And now, in order to do that, so just to what's this quantity roughly? Does anyone know, for an NH bond, what is the magnitude of this quantity in hertz? What's the maximum for a 1 angstrom NH bond? Roughly.
11 kilohertz.
No. For the NH, it's more like 24 kilohertz. Somebody calculated. I'm pretty sure it's 24 kilohertz. If you have a 1 angstrom for an R of 1 angstrom, the dipole coupling between the NH is something like 20, on the order of 24 kilohertz, which is massive, of course. And is that field dependent? Because there's no magnetic field term in my equation. And so 24 kilohertz is a very big number compared to your typical solution NMR dispersion of chemical shifts. So we want to shrink that number down. We don't want 24 kilohertz worth of dipole couplings. That's a problem. We want dipole couplings on the order of what? 24 is too big. How small would you like them to be? Like take them down by a factor of 100. So with 240 hertz. How much is what's the size of an NH scalar coupling? 90 hertz.
Yeah.
So you want to add 240 hertz on top of 90. I mean, that's reasonable, but the problem is that at that level of alignment, protons will have, protons that are 3 bonds far apart will have a very significant dipole coupling. So you're going to still get multiplets and multiplets. Everybody's being dipole coupled. So you want to go further down to the level where, let's say, the nitrogen experiences the proton dipole coupling, but everybody else is not significant. I mean, you can always try to deal with the complexity of the spin system, but 90 hertz is your typical J coupling. Say on the order of 20 hertz maximum, 20 hertz or 24 hertz. So that means that, you'll measure in NMR, you'll measure 90 plus 24 hertz. So to get 24 hertz instead of 24 kilohertz, what sort of alignment levels do you need? If you have 100% alignment, you get 24 kilohertz. To get 24 hertz, you need 0.1%. So you want, on average, of course, there isn't like one molecule that's aligned and everybody else isn't. But the distribution of orientations is such that, roughly speaking, one molecule in 1,000. I mean, you could go down to 2 hertz. If it's 2 hertz coupling, so what puts the limit on how small it can be, the dipole coupling? So the limit on it can't be too big is given by the complexity of the spin systems and the fact that you end up with lots and lots of dipole couplings that you want to keep at bay. And I'm telling you that you are probably going to get alignments of 10 to the minus 3 for that. Otherwise, you're going to start getting lots of long-range dipole couplings, complicating the spectrum. But what's the lower limit of how low you can go? Why can't we measure? What's the smallest? The line width is a good estimate for that. Although you can beat the line, the precision with which you can determine the center of a line is not the line. It's much smaller than the line width because you can integrate the data, etc. So, but roughly 10 times better than line width. Is that how well you can determine the center of a beacon? Let's say that's, but it's roughly given by that because that determines the precision with which you can measure the contribution. If the contribution is smaller than the precision of measurement, then there's no point measuring. But so anyway, so 10 to the minus 3 to 10 to the minus 4, 10 to the minus 5 would be the range where we could begin to maybe make some progress measuring these dipole contributions. So you need the right degree of alignment. You can't have too much alignment. You can't have too little alignment. Too much alignment, you can't apply spectra. Too little alignment, it's hard to measure. So I'm going to quickly, just because I find this super fascinating, history. That's the first thing I did as a grad student, by the way, write the history of alignment. This is a long-standing effort, by the way, in the NMR community to do this. This is not like new. It started in the 60s. And actually, the first experiments involved electric field alignment. And I just came back from ENC and read and saw a talk where people were using electric fields to align molecules. I don't know if you were there, Art, at the ENC.
I didn't see that one, but these guys all know that they had a student.
And Anne had one of the very early, this is many years ago, right? One of the very early studies of Anne's were involved in electric field alignment. And so anyway, so it started, as usual with NMR, you always often start developments with small molecules, small organic compounds, and you do various things with them. This is also the case here. And so the idea was that you could align something with electric fields was in the 1962. And the first anisotropic measurement of a partially aligned system was dipole couplings in nitrotoluene using electric field. And so this was the demonstration, the proof of principle for demonstration that you can partially align molecules with the use of electric fields. And then the theory for how you deal with, as usual in NMR, everything is something new. There's always a tensor that goes with it. And the probability distribution of orientations or the alignment of molecules is described by a tensor, which originally was called the Soppe matrix. Now we call it the alignment tensor, but actually it's Soppe and Englert who derived the equations that demonstrated that there were really only 5 numbers you needed to know to account for the averaging of a rigid structure under the influence of partial alignment. So that was the theory of how you would explain the data. And then they also took a benzene sample and dissolved it into a nematic liquid crystalline substance. So these liquid crystals partially align themselves. And when you put benzene, simple molecule as benzene, into this aligned matrix, all of a sudden the spectrum was super complex. You'd see benzene having like dozens and dozens of resonances arising because of the dipole couplings that were demonstrated. So this was the initial demonstration that you could use ordered media or aligned media to impart alignment to a solute. And then later on, there were measurements done on quadrupolar splittings, but the quadrupolar splittings are huge. This quadrupolar interaction is a very big interaction. Why do we hate it? What?
It's at least hundreds of kilometers.
It's hundreds of kilometers, so why not measure quadrupolar interaction? Why not measure? Aren't they wonderful things to measure? The quadrupolar couple, why not? Quadrupolar relaxation is horrible. So there's a trade-off. So so quadrupolar relaxation makes alignments much greater, making it not the best bang for your buck. Okay, so then comes measurements of magnetic alignment. So you can also so you can apply an electric field. I should have said this. You can apply an electric field, and if your molecule is not has an electric dipole, then there will be a preferred orientation for the molecule relative to the applied electric field. Now, if your molecule has a magnetic susceptibility tensor or an anisotropic magnetic susceptibility tensor, meaning that it has magnetic anisotropy associated with it, by a similar mechanism, you can magnetically align such molecules. And a lot of aromatic compounds, for example, because of the pi electrons circulating around, creating a magnetic anisotropy tensor that's generally normal to the plane, they end up partially aligning. But even more are paramagnetic systems, where generally speaking, for these molecules, paramagnetic susceptibility tensors are 10 to 100-fold more greater. Again, it depends on the molecule, but if you have a paramagnetic metal center, the magnetic anisotropy is much larger than the diamagnetic counterparts for these compounds. So not too surprising, you have paramagnetic system and quadrupolar splittings being the first example of magnetic alignment, because you measure the big thing using a paramagnetic alignment. And then Bodmerby and others showed that you could measure magnetic alignment in paramagnetically aligned compounds. So the first RDC measurement in a magnetically aligned molecule was done by Bodmerby in the context of a paramagnetic system. And then things continue, and I just want to point out that the first measurement of an RDC in a biopolymer, this is something that most people don't know, was also done by Bodmerby on a nucleic acid. So many think it's myoglobin where the first RDCs were measured. That's actually not true. The first measurement, and it's reported in the thesis, is by Bodmerby, who took a DNA, and in DNA, the bases are each little high magnetic anisotropy, and so when you stack a bunch of bases, you get a large net magnetic anisotropy, which can be used to induce alignment, and the dipole couplings were measured between H5 and H6 protons on a cytosine level.
Was that done the 600?
Yes. I think it's either 6 or 5.
I think Macromolecules had the first 600.
Could be that was, and so by the way, if we think about how does magnetic alignment scale with the magnetic field? Let me ask that question. So if I double the magnetic field, how much more aligned is my sample, which has magnetic anisotropy? Does it just double? Are you looking it up online? So what happens is you've got let's say this is a benzene ring, and I have a magnetic field. The magnetic field causes circulation of the electrons in such a way that generates a magnetic moment on the benzene. The size of that moment is dependent on the magnetic anisotropy of the magnetic susceptibility tensor. So the benzene has its intrinsic magnetic susceptibility tensor, it has an orientation. And so depending upon the magnitude of the magnetic anisotropy, when you put it in the magnetic field, you're going to induce a magnetic moment. And that magnetic moment, its size depends on what with respect to the field. The bigger the field, and that's a linear. But that's not the game. We're not done. Now the magnetic moment, the induced magnetic moment, interacts with the magnetic field to induce the bias, right? In certain orientations, depending on if you're diamagnetic, you have a magnetic anisotropy, you want to be like this. If you're paramagnetic, you want to be like that. But this interaction, this biasing energy is itself given by, is linearly dependent on the magnetic field as well. So you end up with a B squared dependence because the magnitude of the magnetic moment you generate scales with the field, but then the interaction with the field scales again with the field, and you end up with a B squared. Yes,
What was the magnetic field strength?
I think Art was asking
Maybe
that.
it was
Yeah.
600.
It might have been 600.
So you just took DNA in aqueous solution, put it inside a 600 and it away.
Absolutely. That's one of the first things I did in New York City. All right, following these others. Yes, we'll talk about that. Nucleic acids align by themselves because of the fact, and I'll go over that a little bit. Yeah. All your paramagnetic proteins will align too, spontaneously.
Yeah, but like this magnetic susceptibility of this thing is the same thing as shielding, right? How is it different from shielding?
No, it's not the same thing as shielding. Actually, because if it were, then you would be able to determine the magnetic susceptibility from the chemical shift, which I know you can't.
Yeah.
And there's these cotton experiments that one uses to get at the. I think it's a bit more. It's an interesting question, but I don't think that the magnetic susceptibility is direct because there's only one magnetic susceptibility for the whole benzene ring, you know. So it's not a feature of the nuclei by themselves. It's a macroscopic term that describes the behavior. It's a macroscopic phenomenon, you know. So I don't think so. It requires the collective behaviors of all the electrons over
It's
the.
dominated by reflection. Shifted. And what else is dominated by things? Pardon? Most people would know Boxner body for another experiment. That's famous for. He invented the Rosie experiment.
Is that true? I didn't know that.
He called it camel spin. He was a very.
He likes horseback riding.
Camel spin?
No, he liked horseback riding.
He also liked figure skating. So a
Interesting
camel
guy.
spin is when you pull your arm as if you, and you rotate faster. And somehow he
Oh.
thought that was reminiscent of spin locking. So he called it camel spin, actually made it Rosie.
I did not know that.
Which then took off.
But eventually he won the Laukian for this,
Yes.
not for this. So, and I didn't know that you call it, I always pronounce it Wagner by.
Yeah, I'm not sure.
So then, again, not very well known. Another measurement of RDCs was done in the nucleic acids. This is Bolton, who's at Wesleyan. And he did a similar study where he measured in a labeled sample CH dappled the same year that Jim Prestigard, who was my PI, showed the possibility of measuring RDCs, dipole couplings, in paramagnetically aligned myeloid. And these RDCs were on the order of 2 Hertz. So the alignment levels were not, by the way, all these alignment levels are 10 to the minus 6, 10 to the minus 5, these magnetic alignments, which are not quite as high as we would like them to be. But the measurements were done with very high precision, plus or minus 0.2 Hertz. So you could measure 2 Hertz with plus or minus 0.2 Hertz. So this was really a seminal contribution because it really showed that you could take proteins and align them and measure the RDCs for them. And then another breakthrough happened soon after. The following year, Bax and Chandravedi went back to the SAPE approach of using a pneumatic liquid crystal and use something called bicells, which behaves like a liquid crystal, and they diluted the typical. So normally bicells, which were invented by Jim Prestigard, are used at very high concentrations, in which case you get very high alignment. And what they did was varied the composition of the bicells so that you could get them to form a dilute concentration. dilute by a factor of 10. They had to play with the lipid mixtures to make sure these things still behave in a line. And then when you take a protein and you embed it, so these things will align spontaneously, these bicelles that are used to mimic membranes. And then if you add a protein in there, the alignment is transferred to the protein by mechanisms that we'll discuss. And you could tune how much alignment you have by varying the concentration of the bicelle solution. So this was really a breakthrough because now you could put in any macromolecule and measure these juicy RDCs that are 20 hertz large. And so here's a depiction of two commonly used aligning media. So at the top, we have the bicelles, which are these disc-like membrane bilayers, which when you increase the temperature, spontaneously align. And when they align, your molecule in there will receive the alignment in a way that's dependent on the concentration of the bicelle. So the experiment is you measure your spectra at low temperatures where things are isotropic, and then you measure them again at high temperature to get the aligned spectrum. That's a good question. It's sort of like a phase transition. And so something happened, there's a critical temperature. I don't really fully know. Maybe Art knows.
Yeah, there's a phase diagram.
Yeah, there's probably some phase transition.
And you know about backs of celery?
What?
Backs of celery?
No.
Yeah, I was told it. I've never asked them. Actually, if you go back to just measuring magnetic alignment of ubiquity, there's the small part that's caused by the alignment of molecules hitting the walls of the NMR tube. And it's quite small, but it's real, just like this.
Yeah.
This collision, the molecules anisotropic. It tends to align. So Bax had the idea, apparently, of very small capillars that you would use
Cause
to get alignment, steric alignment walls. And somebody told me once he had the idea of trying to get the fibers out of celery.
there are so many rumors. So I want to.
Molecules up into the celery fibers and then pack them in the NMR tube.
Yeah, so I was a graduate student when Bax's science paper was submitted. And I was asked to look at it together with Joel, this other guy. But prior to that, there were rumors about Bax had shown in NMR meetings, look at my beautiful spectra, look at my juicy 20 hertz RDCs without telling anyone how they were achieving that alignment. And there were all kinds of rumors circulating. Weird that this was a partnership with Kodak, like the photograph, camera, and there was some kind of film involved. It was like a miracle that he was able to tune. He's like, I can change the alignment. I can get 20 hertz, 10 hertz, 30 hertz. So at the time, it was so like, we were all wondering. And it turns out it's literally the same. So my advisor, who invented bicelles, which is what Bax used, was trying to do exactly what Bax did, but unsuccessful. And in the end, it turned out to be just exactly what we were trying, like literally the other student was trying, but we hadn't diluted the system enough and hadn't figured out how to vary the ratios of two types of lipids that go into these bicelles to ensure that they get enough curvature. So, so that was, but I think it was a win-win for the field. So it was okay. Okay, so now there's
You're developing methods. You have to realize there's always somebody else doing the same thing. I'm never thinking that, well, we got lots of students said, if I had known someone else might have been interested in this, I would have worked harder. There's always someone else.
That is true. Now there's a whole plethora of different ordering methods that you can use to align your samples, and these have different compatibilities with temperature, pH, salt concentration. And I'm not going to go over all this, but you can consult this review from Jim Prestera will tell you what's the appropriate alignment needed. For nucleic acids, this is, by the way, these are phage. This is what's called the PF1 phage system, which is basically like the genome of phage, which is a piece of DNA with a bunch of proteins on it that forms these long rods, which align with their long axis parallel to the magnetic field. And these particles are perfectly suited for nucleic acids. There's never a problem using them, and they're pretty stable over a broad range of temperatures and pH. Not every pH, right? I mean, I think below 5 they'll crap out, but they're pretty stable. So that's
You don't know this, Dinshaw left behind this 400. This longevity. And Nan has a friend named Lauren Day, who used to come up and put filamentous phage into the 400 to magnetically align them for doing fiber diffraction. And then when the paper came out on alignment with phage, I thought, why was I not paying attention? This guy was here week after week aligning phage in the 400.
You know, it's a big industry. You know, Asla sells I don't know how he patents it, but they make a lot of money selling phage for this purpose.
So you also have to pay attention.
Now, so another, so now you have this pneumatic, this system that's aligned, it's ordering medium that is aligned by virtue of the magnetic field. Well, it doesn't have to be induced by the magnetic field. There are gel systems where you can compress a gel matrix and determine the alignment based on the way you apply pressure. But let's just say we have a system that's aligned. You put a molecule in there, it gets them. So what's the most reasonable mechanism for alignment? Like, why is my molecule, I mean, as Art said, there's a wall in the NMR tube, right? Does that induce alignment? Apparently it does a little bit. So why would the presence of an aligned thing transmit to a solute which itself is not aligning? So here's a pen. So let's say I have a wall that's pretty big relative to the size of the molecule. Because these particles are quite large. But let's just make them large. Let's make them as large as a wall. And so here my molecule is sampling every orientation just fine. And I get closer. I get closer. I get closer. And there comes a point, let's say here, where notice I'm not a sample. I'm strictly forbidden from sampling. And when I'm stuck there, these are the only allowed orientations. So you can tell that purely based on sterics. And depending on the shape of this, if this was a ball, would anything happen? No. There would be no reason for it to have a disturbance on its orientational distribution. But even for this simple example that I just gave you, yeah, sure, you will experience some bias based on such a simple model. I have to say, I would have thought things are much more complex than that. You know, there's charge, there's lots of things that make the interaction potentially much more complex than the simple mechanism that I described. But quite literally, Advax and Marcus Spectroscopy, after they initially aligned ubiquitin, they took the ubiquitin molecule and literally drew a wall and just, as a function of distance, sampled every orientation, and so all the orientations that are random, the dipole coupling averages to 0. You can calculate the dipole coupling for each orientation, right? So you take this, every vector has a particular angle with the field. You can calculate the function that I showed you, change the orientation, calculate the function. You know, I just do that with a certain grid, like I think they were rotating 1 degrees. And then when you hit the wall, there's a certain amount of steric exclusion. And that model worked remarkably well for the BICEL system. And it turns out that this steric mechanism for alignment works quite well for nucleic acids, but not necessarily for all proteins, because there is an electrostatic contribution, which is much more complex, that can also contribute to the transmission mechanism. So if your solute is charged and the aligning medium is charged, as is the case for phage is negatively charged, then you'll get an additional electrostatic contribution, which Marcus Spectroscopy did model in subsequent work, but it's a bit more complex and the modeling is not as accurate. But the steric mechanism, I think, works quite well for nucleic acids, and it's just remarkable that something that simple could explain. I mean, they could predict the ubiquitin RDCs to within like 0.5 Hz, you know. So this was a very big and important explanation of the mechanism. Yeah.
So, doesn't disordered proteins
We compare that to.
Say again?
But it's disorder protein.
Yeah.
We compare them.
So you tell me, so you have a disordered protein. What will happen to it? So imagine you're sitting on a bond vector on that protein. And it's disordered. And you're going for the ride. What's the likelihood that your orientational distribution relative to the field is random relative to a more rigid, well-folded protein? Who's more likely to be random? Right.
But the argument
Yeah, so because, like for example, if this, imagine there's a bond vector pointing this way. Okay? That bond vector is special because when I hit this surface, it's always perpendicular and it's enjoying a nice juicy RDC. That's great. All of a sudden now I change the shape of this pen because it's disordered and I created an alternative shape. Now the vector will not enjoy the same coherence, and it's going to have a different distribution of angles. And now all of a sudden you're going to start sampling more of the broader theta squared theta minus one, and at some point you get back to zero, So the alignment is based on the anisotropic shape. So in order to get aligned, you have to be anisotropic. And if you start messing with the shape and creating disorder, you're going to start averaging the dipole interaction, just like in the solid. So in the solid state, if you're trying to do a cross-polarization experiment, does it work well for a disordered region? No. Why? Because the disordered region is isotropically averaging conformationally, so that the dipole interactions become smaller and smaller. So for the same reason, something that is disordered will have a harder time attaining a dipole coupling that's measurable because of the combination of the fact that the alignment is more random, but also the dynamics are conformationally averaging over the theta squared theta versus 2. So utility disordered proteins can be aligned, but you would expect that they would need more aligning medium to achieve the same measured rho RDC, So if you need 20 mg per mil for a folded protein, maybe you need 30 mg for an interesting disordered protein. But they can be aligned, absolutely.
I mean, there's a maximum flexibility that part.
It's a great question. Yes. So what would be maximum flexibility? Well, how would you like to define? There's no time. So for RDC, for this discussion, by the way, other than the averaging has to happen at a rate faster than the dipole interaction itself, which again, depending on which regime you're in, solid versus solution, is either 24 kilohertz or 34 hertz. So, but besides that, the time is not part of, so we shouldn't use the word dynamic. I think Art yelled at me once. I think Art was the only one that, like, I've always used dynamics in a general sense to reflect, to talk about things that are moving and changing. But Art once said, oh, you can't use dynamics unless it's a notion of time. And many had told me this before, and I disagreed with that. But I think after, when you said this to me a long time ago, and then Art said it, I was like, oh, this is kind of annoying because that's an MR person saying it. I don't listen to the other physical chemists who typically have this issue, But anyway, so I'm just veering off. But there's no notion of dynamics here. There's no time other than the fact that the Hamiltonian is being averaged out. So this is faster than the interaction. So what would you define to be, if I have a bond vector and you want it to be maximally flexible? I mean, we're only talking about the orientation, right? We're not talking about vibrations. What would you categorize as maximally flexible? What would the bond vector? Let's say, this is not a very flexible bond vector, but what would be a super flexible bond? What would it do?
It would sample.
So it would sample all orientations with what probability? Equally probable. So on a sphere, if the bond vector is anywhere with equal probability, nobody can be more flexible than that. Even if I begin to make some bias in one direction, said new vector is more rigid because it's not as perfectly. Okay, so what's the consequence? What is the dipole coupling for a vector doing what you just said? It's zero. So there is, so the max, that's the same thing as the NMR order parameter. You know, the S squared, it's got a similar functional form. So yeah, so zero is the maximum flexibility. It means you're isotropic, you have zero bias, you have no restraint whatsoever in a sphere, and you're sampling all orientations equally. Okay, so now how do we measure these? So I didn't say this because I didn't go. So the functional form of the Hamiltonian or the dipole interaction is very similar to the scalar couplings. What that means is the dipole couplings will manifest themselves as splittings of resonances. And when something already has a scalar coupling, like a CH bond might have, a one bond directly bonded scalar coupling, the dipolar coupling, the CH dipolar coupling, the RDC, will just simply add. It won't generate a new splitting because there's already a CH splitting. It's just going to add to the pre-existing splitting, and therefore either make the splitting appear bigger or smaller, depending on the relative magnitudes and signs of the scalar coupling and the dipolar couplings. For example, what is the sign of the CH scalar coupling? Okay, what's the typical size of a CH scalar coupling? Okay, how big is it in hertz? Directly bonded carbon proton. Yeah, so let's say 140 hertz. It can be 200 hertz. Let's say 140 hertz. What's the sign? Yeah, scalar couplings have a sign. Now, is the scalar coupling something you can determine from the diameter ratios? I think it's dependent on the art, isn't it? Yes, for well, good. I think it's yeah. So CH have the same. So we have two positive diameter ratios. So the scalar coupling is positive. NH, the scalar coupling is negative. Isn't that interesting? Yeah, the NH. So therefore, this is very important, and probably many papers are retracted, or because somebody is measuring. So imagine I have an NH splitting, and then when I align my molecule, the splitting grows. Now, what is the sign of the dipole coupling? It's negative, right? Because you're adding to a negative number. So you've got to be careful about it, because to translate to the RDC, you need to take into consideration the contribution to the splitting can only be analyzed with the knowledge of the sign of the scalar coupling to begin with. In fact, dipole couplings are often used to determine the sign of the scalar, where it's not easily determinable from the diameter ratios. Like if you have proton-proton couplings and things like that, people have used the dipole contribution to determine what was the sign of the scalar coupling. So so you take your sample, you partially align it, and then you measure the splitting, the scalar coupling between the directly bonded scalar coupling, for example. And I'm showing you an example. And the difference between these two is your dipole coupling. But you have to always remember, so for the CH, the J coupling is positive. And so here you can see in red, we have an aligned system where the splitting grew by 15 hertz. So the dipole coupling is positive 15 hertz. But you do this in the solids. Oh, no, you don't measure the sign. You measure always the distance modulation. I don't think you care too much about the sign. Well,
But I mean,
in your real experiments, you might have like this versus that, depending on the. Well, no, I guess scalar coupling's not factoring in, so forget together. Okay, so these are just alignment media that are especially useful for nucleic acid. That's what we need to look at. Okay, so now you can measure RDCs between a wide variety of nuclei. You can measure RDCs between nuclei that are not bonded at all, or that are single bond, two bond, three bond, or non-bonded, right? Because these are two space interactions. But in general, there's a preference for, like in any experiment, what's the number that you want to maximize? So if I tell you, you have 7 options of RDCs to measure, which number would you like to have? This could be true for any experiment. What's the, they're all valuable. Every vector is wonderful. Any vector is wonderful in the molecule. So what determines like the quality of the RDC I'm going to measure? What's the trade-off? What's two numbers that I care about? So any measurement I make a measurement, and the precision of the measurement or the accuracy of the measurement is determined in part by the magnitude of the measurement and the uncertainty of the measurement. So what would be the ideal measurement? What would be the ideal thing to measure? Something that is what? Big or small? Small RDC or big RDC? Big. What about the error? You want it to be? Okay, so what determines the size of an RDC? If I have a molecule that's aligned, here's the equation again. So, what would make for great vectors to measure? What are the variables that we're going to consider? Distance. So what do you want for distance? Make it as big as possible. Singly, you're not going to get better than singly bonded nuclei. What's the distance between an nitrogen or proton and an H bond? You guys? Yeah, 1.04. Depending on who you ask, if it's mostly averaged or not. But it's roughly the same thing with CH bond. So although CH bonds are like more like 1.1, 1.08. So CH bonds are a tiny bit longer, but it's something that you care about. So okay, directly bonded things are wonderful. What other parameters do we care about? So what would be great? Proton is great. What about carbon? Is carbon better than nitrogen? So here carbon wins, right? You'd say, oh, better off measuring CH bonds than NH bonds because the CH bond would be bigger. Okay, and then, so that's the magnitude. Now, you would like to have the vectors oriented in many different directions, like measure things on side chains, backbone, peptide, C alpha, H, all of those guys. And so protons, again, are going to be a wonderful nucleus to target. It's also one that we usually run HSQCs on, so this is not a difficult thing to do. But now comes the precision, the uncertainty. So what determines the uncertainty of the measurement? The error for different nuclei. We just all agreed CH wins the day, right? CH bonds are wonderful. You can't have directly bonded HH, right? The distance are 3 angstroms or more, and that more than counteracts the benefit of the gyro magnetic ratio. Also, HH couplings are a pain to measure. So, but besides, what determines the precision of measurement? Yeah, the data, but like if I have a position of a line, what aspect of the line tells me how well I can determine the center of the line? The line width, right? Broad line, harder to determine the center. That is what determines the length, the breadth, the width of a line. What's the phenomenon?
Relaxation. T2.
T2. So of course you might care about T1 because of the recycling time of the experiment. So now who has a better T2? Nitrogen or carbon? Well, you'd have to know the CSAs. Let's make it fun. So let's take the sugar carbon, which has hardly any CSA relaxation. So let's say there's no CSA. Let's ignore the CSA relaxation. Who would enjoy the better relaxation problem?
Weaker dipole. Yeah.
So you see which is the opposite.
Yeah.
So the NH will enjoy better T2s because of the weaker nature of the exact interaction, which on the other hand is something that's interesting, right? So there's an interesting trade-off. You can try to make the coupling bigger, but that will come at the expense of a bigger dipolar interaction to a T2. And you can do the analysis and probably this will depend on the correlation time of your molecule and the accounting of the CSA. So it's not a trivial, what I'm trying to say is it's not a trivial thing. The nitrogen magnets are better than carbon. So just because the CH bond, the RDC is bigger, doesn't necessarily mean that that's the right quantity to measure. It's all the best thing to measure are things that have the biggest magnitude to line with, and they're not always co-aligned, those two factors. Things that get big backward couplings tend to also contribute to T2 relaxation. And so it's not an obvious thing to move forward. But nevertheless, the general rule of thumb is you care about directly bonded things to protons. Those are the things that are going to give you the biggest RDCs, and you'll have, depending on the T2 relaxation properties, you're going to get, for example, the sugar carbons have no CSA, very limited CSA relaxation. So they enjoy quite nice T2s, whereas the base carbons and nucleic acids have a pretty substantial CSA contribution to relaxation. So they get broader, not as nice. But overall, you want the directly bonded couplings, which you can see here are in thick lines that have the biggest magnitude RDCs. And then, as Art mentioned, one of our colleagues passed away from a few years ago, passed away a few days ago. And one of his contributions was developing experiments. His name is Vladimir Sklenar. He was from the Czech Republic, and he invented the Watergate sequence, which I think probably most of you know and are using. And he made many important contributions to nucleic acid NMR, including experiments for measuring many of the couplings shown here, which involve carbon-carbon or long-range carbon-nitrogen RDCs, and really developed a wonderful suite of experiments for these sort of longer-range couplings, which are hard to measure because they're smaller, intrinsically smaller RDCs. But he took advantage of the fact that some of these carbon nuclei in bases have no protons attached to them. So they enjoy actually quite nice relaxation properties, and developed a suite of experiments. It's still a pain in the butt to run those experiments because they're, the trade-off is still not great, but I figured it would be good to just mention it and mention its contribution. Same thing goes with proteins. So again, the NH bond, 20 hertz, then the corresponding CH bond would be bigger, and one can also have longer range interactions. These carbon-carbon. So carbonyls have wonderful relaxation properties. So, these are small RDCs, but you can take advantage of the favorable relaxation from carbonyls to measure them reasonably accurately. But there's a whole range of networks of couplings that one could measure. Okay, so how do we measure? Now here, so now you can do your product, you can put your product operator formalism knowledge into practice. So we still want optimal experiments to measure those splittings or J-coupling. And prior to RDCs, there was no real reason to measure one bond coupling. I mean, nobody really cared. But one bond scalar couplings have very interesting information. Like you could, in nucleic acid, like this J-coupling is strongly correlated to the dynamic of like the order parameters. I think Nico Chandra showed this. We see it also. The more dynamic the nucleic acid, typically our scalar couplings are smaller. These are just J couplings. So, but okay. But in general, one bond scalar couplings were absolutely of no interest to anybody because there was no dihedral angle, unlike 3-bond couplings where you have the intervening dependence on the intervening dihedral angle, and there was reason to measure that. There was really no reason at all to measure one bond or these 2-bond scalar couplings, except for RDCs, and that led to a whole swath of experiments that are optimized to get your position, your line positions as accurately as possible. And so I want to go through a few schemes, and maybe for the Art, you said there was a workshop or there's a problem set. Is that what I could do tomorrow?
Problem set session is usually after this class, but you take time tomorrow.
Okay, so maybe we can walk more rigorously through the product operator formalism, some of this. But I'm also going to teach you my system for analyzing pulse sequences, which is the poor person's system that I think is interesting. See if I even remember how to do it. It's been a long time. So let's imagine I have a system where I have I and S. So this would be I would be proton as usual. S could be carbon or nitrogen. And normally in an HSQC, so this is T1, the initial period. So I have the inept element that I'm removing from my scheme here. So I have an inept sequence, which transfers magnetization from I to S. And now I have, so what do I have here at the end of an inept? What's my product operator?
I see.
IZSX. Or SXI, it's IZSX.
Sure.
No, you have to order it correctly. It's IZSX. Yeah. God, SXI is really horrible. Okay, IZSX. Okay, so now I have IZS, so I have IZSX, and now I have this evolution period. And I want to figure out what ends up happening. It's an unusual period. It's an unusual sequence, right? And I want to figure out what happens to my magnetization and what spectrum might I expect. So let's walk through this. Let's start with chemical shift evolution. So my system involves breaking down evolution into scalar coupling evolution and chemical shift evolution. So let's start with chemical shift evolution. So my magnetization begins to evolve, and remember, when I apply a 180, if I apply a refocusing 180 pulse to my magnetization evolution, I start precessing the other way. Now, in order to account for that, we're going to subtract time, and I'll show you how we do it. So let's start off with just chemical shift evolution of the SX or IZSX magnetization. So it evolves for period T1. Agree? For period of T1, so I would write in my little notes plus T1. Chemical shift has evolved, is going to evolve for plus T1. Okay. Then there's this term here, kappa T1 over 2. Yeah, it will also evolve for that period. So we write T1 plus kappa T1 over 2, adding them. Now I'm getting hit with the 180. So when I get hit with the 180, I'm going to start processing the other way around. So I subtract the remaining period. So now I do minus kappa T1 over 2. Are you with me? So that is the period. This is the chemical shift evolution. Whenever I see a 180, subsequent period, I subtract. I put a minus in front of it. And now I tally up the periods. What is the chemical shift evolution? T1. So therefore, I can already say it's cosine omega T1. You know, cosine omega T, little T1 is the evolution that's going to occur. So that's chemical shift. So that's very good because that's your normal chemical shift evolution, right? We always want chemical shift to evolve usually as T1, little T1. Right? Remember, T1 here is being incremental. And if something is a function of T1, it will appear as a frequency in your spectrum because if you transform relative to T1. If you have a cosine modulated T1, you're going to get a nice frequency. Right? Now let's ask what happens to ISJ coupling evolution. Okay, so now, same question. Now we're going to ask how much does the scalar coupling evolve? And so again, T1, good, plus kappa T1 over 2. Oh, but now look, I have two simultaneous 180 on both the I and the S. Does the J coupling reverse or stay? It stays because I'm putting 180s on both of them. Right? So J coupling evolution continues. If I had only one 180 on the carbon nucleus, on the S nucleus, then I would refocus J couplings as well for that period, just like a chemical shift. If I had one 180 on the proton, I would also refocus it. But when I put the two, I flip both of them, and so the coupling evolution remains the same. So what is the total scalar coupling evolution? It's T1. So T1 plus kappa T1. Let's make kappa 1. Let's just make kappa equal to 1. What I find is my chemical shift evolved for T1, but the J coupling evolved for 2T1. 2T1. Because kappa is 1. So you're going to add T1 over 2 plus T1 over 2. That gives you another T1 plus T1, so you get 2T1. Yes. So how does that differ for my situation. So I have chemical shift to T1, J coupling is 2T1. Versus chemical shift to T1, J coupling is T1. How does the spectrum differ in appearance when I Fourier transform it? So I magically created 2. By how much? Because remember, it's usually cosine pi JT, cosine pi JT1 versus cosine pi JT1. So what has happened to my J artificially? It's double. It's actually a wonderful. It's a wonderful. So you measure the spectrum, and literally, because you remember how we've been talking about, we want bigger things. The bigger the magnitude, the better. So now you've doubled artificial. I mean, by spin dynamics, you've apparently doubled because you're spending more of the time evolving the J couple and less of the time evolving the chemical shift. So there's a trade-off here. You are spending a lot of time. The duration of the sequence is long, so you're getting relaxation. But you're deciding, I care more about the J coupling than I do the chemical shifts. It's a trade-off. You can choose to do that. Now you're going to lose chemical shift resolution because you could have used the whole period to allow a longer chemical shift evolution, ultimately. But the trade-off is you get better scalar. So you could work out through the product operators for this. I mean, it's trivial, and discover. And you could change kappa, make it 1, make it 2 or 3, and you would double the couplings or triple, and therefore get more accurate precision measurements of the system. So now, what if so? By the way, I ignored here any other couplings. For example, the NH, the N might be bonded to a C. So let's say the nitrogen is bonded to a carbon, and I don't want nitrogen carbon integration, right? That would be bad. How do I do that? How do I take care of it? Let's say I have a nitrogen and it's coupled to, in proteins, nitrogens are bonded to carbonyls and the alpha. Let's say there's an NC carbonyl scalar company, and I don't want it to evolve. How do I get rid of it? So what would that entail? How would I get rid of give me a pulse. I need to put some pulses somewhere to get rid of the nitrogen carbonyl evolution. Put a 180 on the carbonyl, because this can be selective. And then where would you put it? In the middle, right? And that will refocus. If you do plus for the carbonyl evolution, you would say it evolves plus T1 minus T1, right? Now it'd be more complicated if kappa was not, kappa is like 1. You wanted to put it in the middle of the evolution, but then there's a 180 here. So you have to worry about that, right? Because that's going to then refocus the coupling again.
Should be like the S speed, the coupling with if we have a K speed is the carbonyl.
Yeah.
Then should it be like in the middle of the sequence like here?
Yeah. So here,
Not
so here, let's imagine I have a channel here, which is carbonyl, and I put a 180 right in the middle here. So now let's work out the J coupling evolution for nitrogen carbonyl. For the first period, T1, it's T1. Then you put the 180. Now I do minus kappa T1 over 2, but now I'm hitting it with another 180, so now I have to invert again, right? So that's not going to work. Where else would you put it?
I put it in the middle of the first thing.
Exactly.
Yes.
You put it over here, and you can just work out the numbers that I mentioned to figure out where to put it. Okay, now what if I have carbon-carbon? So you can have a situation where you have carbon-carbon couplings. So you're looking at a carbon, that's what you care about. And the carbon has a beautiful carbon-proton coupling, but it also has a carbon-carbon coupling. And that other carbon is not like the carbonyl, which is very well resolved, and you can enjoy a selective pulse from the carbonyl. It's a carbon that's kind of nearby. Chemical shift pulse. Now you can't just, an alternative would be to use a constant time. Right. And so this could be our, this pulse sequence, which by the way is my first pulse sequence I ever designed as a graduate student. It accomplishes the coupling enhancement, but ensures that the carbon-carbon couplings don't evolve over T1 because it's what's called a constant time experiment. Did you guys cover any constant time experiment? You know, we'll dive deeper into that tomorrow. How am I doing on time? What time is it? 2:30?
It's too concerned.
Huh?
It's
2:30? Okay, well, let me just finish a few more things. So this is the coupling enhancement. So you'll notice that this is applied to our carbohydrate molecule. You'll notice that typically CH bonds are 140 hertz, but now we have 280 hertz because this doubled the appearance of couplings, you know, this coupling enhancement scheme. Then there are, so by the way, there are two classes of measuring splittings. One is frequency-based. Frequency-based methods involve measuring the center of a peak. You know, you have a peak here, you measure the distance, that's your couplings, your splittings. And everything I've discussed so far, coupling enhancing schemes are frequency-based methods. Another frequency-based approach is the so-called IPAP experiment, where you basically, in one experiment, get the doublet like this. Is this cosine pi gt or sine pi gt? Get cosine pi gt, because you know, if I do this experiment, the problem is I have two peaks. I've doubled the number of resonances in my spectrum, and therefore I get crowded. So I'd like to just be able to measure one component in one spectrum and the other component in another subspectrum. So if I do an experiment where I get this type of splitting, where the peaks are cosine pi gt modulated, and then in another spectrum I collect this type of peak, then if I add those two, this and this, I get this. If I subtract them, I get that, and then I can invert this. So that would be a great way of doing things. So this is a cosine modulation, and that's what you would get for the standard inept. If you have IZSX, and you then run your evolution, you'll get the cosine modulation. And then if you have this refocusing period here, you can get the sine modulated, sine pi gt evolution, and then add and subtract. And again, this could be something that we work out in detail with the product operated formulas. There's an experiment that I think Christian invented. Is that right? The ecozy.
yes.
So if you have, for example, imagine these two lines are, their splitting is smaller than their line. So they're like on top of each other. You know, two peaks that are so close because it's closer than their line width, so that they're unresolvable. But let's imagine that this IX spin system, that the X system is also coupled to another S system, another S nucleus. So you've got splittings this way, you've got splittings that way. You can develop a sequence where in one case you get all four positively, and in another case by doing the antiphase, these shaded guys are antiphase or negative peaks. And if you add and subtract, you then can resolve the two peaks and determine the center of this peak without the burden of the nearby peak. So you can get this peak and get that peak, the centers, and thereby measure JIX, despite the fact that otherwise, so you're using another scalar coupling to shift peaks apart to get the target. So you're using JSX to resolve the JIX by this type of topology. And then there are what's called intensity-based pulse sequences, where, so right now, when we say we're measuring splitting, that means I always have a term like cosine pi j little t1. Little t, whenever you see j and t1, little t1 together, that means that when you Fourier transform the system, you're going to get a splitting given by the t1, little t1. But in the intensity-based experiments, what you do instead is you say, no, I'm not going to let it evolve as a function of little t1. I'm going to let it evolve as a function of some number, like capital T minus delta. It could be whatever symbol. So during my evolution period, my J couplings evolve for a defined amount of time that you choose as the user. So let's call it delta. And that term is being multiplied in front of your operator so that the intensity of the HSQC is modulated by cosine pi JT. So then you vary the delta number, and the intensity will be modulated. The intensity of your HSQC will be modulated by cosine pi delta, and then you can fit the intensities of the modulation of the intensities to get the couplings out. All right, so we'll continue tomorrow. We'll work through the product analysis of a few of these, and then continue talking about RDCs.